The tangent in the secant line. The word tangent is derived from the Latin word tan, which means touching. This means that the tangent line to a curve only touches the curve at one point and is follow the same direction of the curve. So if the curve is increasing, the tangent line, the slope of the tangent line is then decreasing. If the curve is increasing, the slope of the tangent line also increasing. Okay. A line that shows 2 points of a curve is called the secant line. The secant to the function f of x to the point a, f of a, and x, f of x is the line passing through this point, and the slope is given by the change in y minus the change in x. So let's see, you are given a curve, and here we have our secant, and is passing through this 2 points, a, f of a, x, f of x. So here we can see that the change in y is equal to f of x minus f of a, and the change in x is equal to x minus a. Now, how do we use the secant line to estimate the slope of the tangent line? Let's take a look at this. Let's say you are given this 2 points. This is called x naught, f of x naught. And this is x naught plus 8, f of x naught plus 8. And let's draw the secant line. Now, think about this. If this, so at this point here we get x naught plus 8. Let's say if x naught plus 8 is moving closer and closer to x naught. Let's say if it moved to, say, here. What happened to the secant line? So our secant line change, and at x get close to x naught or equal, get closer and closer to x naught, keep going and make it more closer, you can guess that the slope of the secant line at x naught plus 8, where 8 is going to 0, then the slope of the secant line is the same as the slope of the tangent line. Okay, so let be the secant line that passes through the 2 points x naught, f of x naught, and x naught plus 8, comma, f of x naught plus 8. Then, as 8 approaches 0, x naught plus 8 approaches to x naught. Right. This means the secant line is approaches the tangent line, and we can use that to estimate the equation of the tangent line. Let's go take a look at an example. Find the equation to the tangent line to the parabola at the point 1, -3. So we need to first start with the secant line. So go ahead and let LS be the secant line. That passes through the point in question and the point 1 plus h, comma, f of 1 plus h. This means the slope of the secant line is equal to f of 1 plus h minus f of 1 divided by 1 plus h minus 1, that equals 1 plus 8 square minus 4 times 1 plus 8. Note that f of 1 is given, that is negative 3. So minus negative 3, make positive 3 here, divided by 8. So let's go ahead and simplify this equation. Like we said earlier, the slope of the tangent line is almost the same, is equal to the slope of the secant line if 8 approaches to 0. So as 8 approaches 0, the slope of the tangent line is equal to the slope of the secant line. As 8 approaches to 0, 8 plus 1 then approaches 1. Would mean the slope of the tangent line equal 1. Now, we have a slope and we have a point. We can write the equation of the tangent line. So then the equation of the tangent line. So then, equation with the tangent line. Y equal mx plus b. We know m equal 1. We want it pass through the point 1, negative 3. We can calculate b. b equal negative 4. This means the slope, so the equation of the tangent line is equal to 1x minus 4. Let's try it again for the next curve. Find the equation of the tangent line to the curve square root of 7 minus x at the point negative 2, 3. Again, let the secant line pass through the point negative 2, 3 and negative 2 plus 8 f of negative 2 plus 8, and the slope of the secant line is given by f of negative 2 plus 8 minus f of negative 2 divided by negative 2 plus 8 minus negative 2, make positive 2. Okay, so f of negative 2 plus 8 is square root of 7 minus negative 2 plus 8 minus 3 divided by 8. So this is 9 plus 8 square root minus 3 divided by 8. So how do we simplify this? So let's go ahead and multiply the numerator by its conjugate and the denominator by the conjugate as well. So square root of 9 plus 8 plus 3 divided by square root of 9 plus 8 plus 3. And we will simplify this. the numerator now becomes 9 plus 8 minus 9. The denominator now becomes 8 times square root of 9 plus 8 plus 3. So 8 divided by 8, square root of 9 plus 8 plus 3. And we simplify this. We get 1 divided root of 9 plus 8 plus 3. Okay, as 8 approaches 0, the slope of the tangent line is equal to the slope of the secant line. At 8 approaches to 0, that go to 0. So 1 divided by square root of 9 plus 3, that equal to 1 over 6. So that is the slope of our tangent line. Now we have the slope and we have 1 point. We can solve for the equation of the tangent line. So y equal mx plus b. So 3 equal 1/6 times negative 2 plus b. So 3 equal to negative 1/3 plus b. b equal 10 over 3. So then the equation of the tangent line is 1/6 x plus 10 over 3. This is y equal. Let's take a look at the velocity problem. This is the one that we're interested in. Let s of t be the position of an object moving along a coordinate axis at time t. The average velocity of the object over the interval at, where a less than t, or ta if t is less than a, is given by the average velocity equal s of t minus s of a divided by t minus a. As t approaches a, the velocity becomes closer and closer to the instantaneous velocity. So what does it mean by the instantaneous velocity? It's talking about the velocity at that particular point in time. The velocity at a particular point. In time, okay? Or at a particular time. Suppose that a ball is dropped from the upper observation decks of the CN Tower in Toronto, 450 meters above the ground. The position of the ball is given by the equation 4.9 times t squared. Find the average velocity of the ball at the following interval: 5 to 5.5, 5 to 5.25. Okay. Part A, in the first interval, 5 sit. The average velocity is equal to s of sit minus s of 5 divided by sit minus 5. 4.9 times 6 squared minus 4.9 times 5 squared divided by 1 equal, and this equals 53.9 meter per second. For the second interval, similar, v equal to 51.45 meter per second. And for the last interval, v equal So look like as the time interval get closer and closer to 5, that the velocities become closer and closer to 15 meters per second. But let's check with algebra. What is the velocity of the ball at t equal 5? Well, let out of S be the secant line that pass to the point, say 5.25, that is the position of the ball at 5.25 after 5.2 or S of 5.25. And this point 5.25 plus 8 and S the 5.25 plus 8. Then the velocity at t equal 5 is estimated by this equation as the 5.25 plus 8 minus as the 5.25 divided by 8 as 8 approaches 0. So let's try this. V equal to 4.9 times 5.25 plus 8 square minus 4.9 times 5.25 square divided by 8. So let's go ahead and simplify this equation. And we'll go ahead and simplify this equation a little more. So as 8 approaches 0, the velocity approaches 51.45 meters per second. You know what I just realized? I estimated the velocity for the ball at time t equal 5.25. Okay, so let's do that. Let's find the velocity for the ball at t equal to 5.25. T equal 5.25. There we go. So at t equal 5.25 seconds, the velocity is equal to 51.45 meters per second. Another application of limit is we use this to estimate the area problem in integral calculus. So we are given the curve. Say, I don't know, let's try with some geometric figure, something easy. Say you are given this geometric figure and you want to calculate the area of this blob. So you know how to calculate the area using the square, rectangle, triangle, trapezoid, and things like that. So you go ahead and you split this into things that you want, that you know how to calculate for the area for. Okay. So you have this blob. You split this into things that you know how to calculate the area for. Something like this. And say you know how to calculate this part. That's the triangle. Here's another triangle. Here's another triangle. So on and so forth. And you be smarter and split this a little more. And you go, okay, I get a little more over here. And then you do it a little more over here. As you calculate the area of all the small part and add it up, you get pretty close to the area of that block. Right? That's the idea. Now, say if you are given a curve, we can calculate the basic figure. We can calculate this. We can go ahead and split this curve into the area into small rectangle. Okay, I can split this into small rectangle. I can calculate this. I can calculate this, and I can pretty much estimate the area under the curve. Pretty simple, right? Well, sometimes I get an overestimate and sometimes I get an underestimate, depending on how I divide in the curve into pieces. But the idea is that as many rectangle that I can fit into it, I can calculate the area under that curve pretty accurately. Okay? So let's try this. Estimate the area under the curve for f of x equal x squared plus 1 over the interval of 0, 3. So let's go ahead and draw this curve. X squared plus 1. So x squared plus 1 is a parabola open upward. So 1, 2, 3, 4, 5, 1, 2, 3. This curve looked like this. It started 0, 1, and then 2, 2 to 6. 3 to 10. Let's try to draw it a little nicer. Okay, so it's something look like this. Okay, and say this is 3. 0, 1, 2, 3. So we can draw the area under the curve the two different ways. Let's start first with this. I can make this area under the curve 1. And here, let's make it under, right? 1. Okay, so these are the part for the area under the curve. Note that since there is this leftover triangle here, the area under the curve is an underestimate here. Okay. I can calculate by taking f of 0 plus f of 1 plus f of 2. F of 0 equal 1, f of 1 equal 2, f of 2 equal 5. So the area under the curve here equal to 8. So this is an underestimate. What if I go for an overestimate? If I draw an overestimate, 1, 2, 3. I can still draw my rectangle, but then the overestimate will be this part. Then we have the rectangle that is above the curve. So this area would be an overestimate. So then the area under the curve in this case will be equal f of 1 plus f of 2 plus f of 3. Okay. Another way you can do to avoid this over and underestimate, you use the midpoint. So you get less of the of an over and underestimate. So let's try this if we use the midpoint. Again, here's our curve. 1, 2, 3, 1. So the midpoint will be 0.5, 1.5, 2.5, right? And we still would draw our triangle, but with the width of 1, with the length of our midpoint. So you still get the area under the curve, but it's a little more accurate. Okay. So then the area under the curve in this case will be equal to f of 0.5 plus f of 1.5 plus f of 2.5. So I go ahead and we estimate the area under the curve using SID rectangle, and I would try to avoid the over and underestimate too much. I go ahead and use the midpoint in the same interval. So 1, 2, 3. And we want to split it into 6 different intervals. So 0.5, 2.5, 1.5. Let's just take a look at the number line itself. So 0, 1, 2, 3. So 6 rectangle, 0.5, 1.5, 2.5. And we use the midpoint of each of this interval. So 0.25, 0.75, 1.25, 1.75, 2.25, and 2.275. 2.75. So the area under the curve using SID rectangle will be the total of f of 0.25 plus f of 0.75, f of 1.25 plus f of 1.75 plus f of 2.25 plus f of 2.75. So this will give you the more accurate area under the given curve. The more rectangle you use, the closer to the actual estimate, the actual area is going to be.